Muy buenas tardes a todos. Muchísimas gracias por estar con nosotros en nuestro 23º Senior Webinar de Alcompat Holcim en la voz de un experto. Estamos empezando puntuales para ver un Senior Webinar, primero en su tipo, que vamos a ver sobre la segunda torre más alta del mundo. Pero antes de eso, quisiera agradecer a Holcim por estar con nosotros ya desde hace 6 años en estos senior webinars muy exitosos. Y bueno, voy a ceder la palabra a Javier para que nos dé su mensaje como eh, colega y socio en estas aventuras. Y luego nuestro presidente, Eño Pacini, nos va a dar la bienvenida. Adelante, Javier.
Gracias, doctor Pedro. Muy buenas tardes a todos. Bienvenidos a este señor webinar. La verdad que yo estoy muy contento y muy emocionado de estar participando en esta gran sinergia que hacemos con Alcompat. Y bueno, pues disfruten mucho la sesión y les cedo la palabra a Enio. Adelante.
Hola, ¿se me escucha bien? Sí. Buenas tardes a todos. Es un gran placer abrir esta webinar, donde ya desde luego agradecemos mucho al doctor Ahmad Abdelrazaq por compartir con nosotros sus conocimientos y además este gran proyecto internacional. Agradecer a Holcim, que nos da la oportunidad de tener esta presentación en nuestra Asociación Latinoamericana de Control de Calidad, Patología y Recuperación de la Construcción, nuestra Alcompat Internacional. Es un gusto tener toda la presencia que aquí se acerca a nosotros de todas las partes de Iberoamérica. Y gracias también a nuestro director general, doctor Pedro Castro. Gracias, Javier. Gracias, Pedro Castro. Y a nuestro palestrante, el doctor Ahmad. Gracias. Thank you very much, Dr. Ahmad, for come here and chair this important project, international big project for the Latin America community. Thank you very much.
Gracias, señor. Voy a presentar. I'm going to introduce now to Dr. Ahmad Abdelrazaq. But before that, probably Ana is gonna be our interpreter. Ana va a ser nuestra traductora, traducción simultánea. Invito a Ana para que pueda abrir su micrófono y comenzar la traducción simultánea. Entonces, voy a esperar a que Ana abra su micrófono para empezar a presentar al doctor Ahmad. Sí, Ana, ¿podéis abrir tu micrófono para comenzar la traducción simultánea? Bien. Voy a empezar y Ana en cualquier momento podrá abrir su micrófono para comenzar la traducción simultánea. Dr. Ahmad Abdelrazaq is going to present to us this senior webinar, Design and Construction of Merdeka 118 Tower using High-Performance Concrete, pushing the boundaries of concrete technology for megatall towers. I'm going to give some words about his CV. Doctor Ahmad es fundador, director general y socio de Rise Global. Es una figura de referencia mundial en ingeniería estructural y construcción de rascacielos. Es fundador y director general de Rise Global. Ha liderado proyectos complejos y emblemáticos en Asia, Medio Oriente y Europa. Fue vicepresidente ejecutivo de Samsung CIT en Corea, donde dirigió el desarrollo de la división de edificios de gran altura. Ha participado en todas las etapas de obras icónicas como el Burj Khalifa de Dubái, que es la torre más alta del mundo, Merdeka 118 en Kuala Lumpur, que es de la que nos va a hablar hoy, Samsung HQ, Kia World Center en India y muchas más. Él previamente fue socio asociado de Skidmore, Owings and Merrill y ha trabajado en proyectos como la Jin Mao Tower en Shanghai y el Hong Kong Convention Center. Él es ingeniero civil por la Universidad de Texas en Austin a nivel de licenciatura y de maestría y es miembro de la Academia Nacional de Ingeniería. Ha recibido numerosos reconocimientos, entre ellos el premio Ernest Howard de la American Society of Civil Engineers. La experiencia de Ahmad combina excelencia técnica, liderazgo global y compromiso con la innovación en la ingeniería de rascacielos. Estamos muy agradecidos con Ahmad por estar aquí con nosotros. We thank you, Ahmad, for being with us this morning. The presentation is yours.
Thank you very much for the nice presentation, and it's nice for you to organize this webinar. It's my great pleasure to present this project. It's this one of those projects where you run into a lot of unexpected challenges. For example, when we started the project, the construction in 2015, the foundation, the tiles were done, but at the same time, we ran into a very difficult time during COVID, in which we have a lot of resources, and the question, how do you deal with that in the middle of construction where many things got shut down. So this is one aspect of it, but for every tall building we do, somehow in the middle of it, you will have some sort of a crisis. So with this one, I think we will today focus on the design and construction planning of this project. When I started working on this project, essentially it was a bid on the project for construction. But then when we looked at the project, there were a lot of challenges from a construction standpoint. So we looked at the project and we decided to propose an alternative design from a constructability standpoint. So the structural design ended up going from construction only to design build, where Samsung was responsible for the structural design and construction of this project, Samsung and UEMGV. Again, this is a great seminar, and I can see great number of people attending everywhere internationally. Now, the announcement for this building at the topic of the when we did complete lifting of the spire in 2022, essentially this project became the second tallest building in the world that's already built and completed at 679 meter. These are some of the images that were taken of the project. And these are just images of the skyline of this project relative to Kuala Lumpur, KL. Is a very dominating this project. As you can see, the site of it, it's which I will speak later, in a very old historic district near Chinatown, and where the whole area has been is being gentrified. Now, this is the Merdeka 118 in comparison to other tall buildings in Malaysia. As you can see, the Petronas Tower was at one point the tallest building in the world at 451.9 meter. And during construction of this project, this where we introduced a very high strength concrete, and really the QAQC program and what was done for this project was very unique. And at that time, the concrete strength was about C80 concrete. And for almost 30 years, nobody has used higher strength concrete until we came in and we used C105, which I will speak about for different reasons. Now, this is here is, as you can see, comparison to Burj Khalifa, which I happen to participate in both design as well as ETSOM and the construction. and monitoring system of Burj Khalifa, which is an old concrete building, and Merdeka 118 is now a composite building, but most of the lateral system is mostly concrete. Now, the developer is a PMP, which is National Investment Corporation, which is in, kind of for Malaysians only. And the employer is PMP Merdeka Venture, and we worked under Dato Tango Abdelaziz, who was the CEO of the project from its inception to completion. The contract administrator were Turner Construction or Turner International Malaysia, where they did the contract administration mostly. Now, some of the consultants include FKA, were the architects of the project, international architect, and RSP were the local architect and of record of the project, and they were the executive architect. And then for civil and structure, Lera out of the US did the schematic design and 50% DD. And Arab Malaysia, in collaboration with Arab International, were the structural engineer and civil engineer of record. MAP Lair out of the US and KTA were the local consultant. The contractor was Samsung CNT, where I was the executive project director on the project, and UEM is our local partner. So it was a Samsung CNT UEM joint venture for developing the design of this project. The project essentially consists of it's a multi-use building. We have 5 parking level, about 20 meters below grade. And then we have the lobby and reception of Baker House up to level 8. And from level 8 up to level 96, we have an office. And from 96 up to about 118, we have hotel and apartment, 112 to 118 apartment suites and hotels. And again, from 113 to the top, we have skydeck and restaurants and VIPs and so on and so forth. The whole project, the top of the roof of the building is 509, but for the architectural top, it's 679 meter, essentially. Now, the site location, as you can see here, is a very important, what we called is the Golden Triangle in KL, which consists of the Petronas Tower, which is at the Central District area, and then the KL Tower, which is this one here. And then the development of Merdeka 118 is a new project that is located in a very highly dense area near Chinatown. And this area has a very big historic significance, but it's also the traffic was awful in this area to get in and out of the area. So the site location, when we started in 2012, this is what it looked like. The site is near very significant sites, including the stadium, which was in a shallow foundation called Nagara Stadium, and then Merdeka 118. This is where Malaysia independence took place. And there is also another sport facility here. So the site essentially had to integrate all of these, bring everything together to gel into one big development project. So the total site area was definitely huge, and it has many activities going on with the infrastructure. Now, the site, when we work on this project, essentially the site is very big to be accommodated. So the client took it on itself as a national company to enhance the infrastructure. So they did analysis for the entire site in terms of traffic analysis, and they decided to add metro stations, a lot of roadways, a lot of infrastructure to improve the overall circulation that was required for the site, and it made the site accessible to the LRT, the monorail. They improved the whole traffic system over the entire site. So essentially, they have a very large number of people, I think, getting into the site using mass transportation. So there's a lot of traffic analysis that was done by the client in terms of access and changing the whole traffic in the area to improve the problem that they had, and order to make the whole thing interesting. Now, in terms of the site, we also have near the site, they were building train station. So imagine you have deep basements, you have train station, you have a lot of Nagara Stadium, we have Merdeka Stadium. They were all in shallow foundation, and we have to weave it through all of this and have a 9-story basement, which made to manage the vertical and lateral movement of the site was extremely important, because we didn't want to affect the foundation. Most of these buildings were on shallow foundation, so any kind of settlement, whether it's vertical or lateral, would have been detrimental to the this project. The architectural design concept of the tower is very much influenced by traditional Malaysian songket pattern, which is signify the diamond shapes, which as you can see is expressed in the outside of the facade, and the spire symbolic image resembles the silhouette of Prime Minister Tunku Abdurrahman Aziz when he declared Malaysia independent in Merdeka site, which near here. So this is one of the significant things that kind of included in the design of this. Now, as Samsung scope of work, essentially to build the site over the entire this area. As you can see, it goes around the Merdeka Stadium, which the independence take place, which is sitting on shallow foundation. Nagara, which is also on shallow foundation. We have a train station that run across there. And then also we have a stadium near here, as I mentioned, all sitting on shallow foundation. The total site area was 76,000 square meter. Our scope of work was civil, facade, architecture, and MEP. And then, as you can see, the blue area was under our scope of work, but all the infrastructure that is going around it under different contractors. So the interaction and also between all the other contractors and the interface was extremely important. We are in the middle of it. And to complicate things even more, the client gave the retail to another contractor. So we are in the middle of all of this, which presented a huge challenge from logistic and coordination standpoint. These are just some of the images where the project was on October 2021 before lifting of the spire. And this is here is the completion of the project in January 2022, when it was declared the tallest building, the second tallest building in the world. Again, where did the design come from? It wasn't a design competition. The client selected FKA as being the architect, and they proposed several schemes. But the client selected the diamond shape scheme, which was from a structural standpoint, as you can see, is not that easy. It's a pretty, it's not the most efficient one for both either wind or even structural arrangement standpoint. Anyway, this is what the office, typical office look like. Essentially, we have a central core, a mega column in the outside, a structural steel framing in the inside, and a small steel column that transfer. And these at the edges of the building come in and out. And this is a typical sky lobby and this typical hotel from architectural standpoint. So the total spire height is about 161 meter. One of the challenging aspects of this project is the wind engineering. When you look at this project, you would think, oh, there's a lot of variation in the shape. And there is a lot of, as you go up the height. So when you first look at it, you get the impression that the wind is not that critical. But as some of you may know, Malaysia is a very benign wind. It's in the equator, and also they don't have much seismic activities. So, however, if you look at the basic wind speed for Shanghai, Seoul, or Busan, or Gwangju, which are very, very high winds, for a building of a similar height, what you can see, Merdeka, which is the basic wind speed in Malaysia, is 35. But because of the shape of the building that you can see here, there was a lot of crosswind response, in which the basic, the bending moment was so high, bigger than any of the other, because of the dynamic response, than any of the other buildings, which presented a big challenge. The other challenge that we have in this building, as you can see here, this is the neutral axis. So most of the material in the core, in the weak axis, is essentially very much concentrated here. And there is very little to magnify the moment of inertia of the building. So in order to overcome this, they put this very big hammerhead, they call it a hammerhead, which is roughly about 4.6 meter by 7.2 meter solid concrete block. And also the mega column here, which is 4.2 by 3.6 meter, which is also huge. And as you can see, these also mega column were not contributing much because they were closer to the neutral axis. And so these columns will have to be even much bigger. To overcome this, the engineers have put a huge amount of rebar. Imagine 4.2 meter by 3.6 meter with 4% of rebar. And they added the rebar for stiffness, not necessarily for strength, which made the constructability very much difficult. It would have been much easier to make them as a composite system, but they didn't. And so these are some of the challenges that we have on the project. So when we came in, we proposed to increase the concrete strength from C80 to C105 and use a special type of aggregate, because in Malaysia, they only use the granite. So we went and found a source in Johor in Malaysia, which is basalt, in which we were able with a much higher stiffness. So the idea is to add more stiffness to the building rather than add rebar. And by doing that, we took out about 14,000 tons of rebar on this building. In terms of the wind engineering, as you can see here, again, the shape of the building is not ideal. It's like an airfoil. And so the Stroll number for this, if you look at that, is roughly about 0.6, and sometimes is even higher. However, if you look at a building that's a square, is 0.12 or so, and which means that we had a lot of dynamic excitation on this building. We did a lot of wind tunnel testing, including high frequency, pressure integration, aeroelastic. I will not spend a lot of time on this because we had to redo some of these during the redesign of the building. And then also, but fortunately, we didn't change the properties much. And also, cladding and pedestrian window studies. So what you can see here is a comparison between, as I mentioned, Malaysia is a low seismic region. However, it's very close to Indonesia, which has a very big earthquake. It's an active area. However, we looked at long-range and short-range earthquake in the region, site-specific analysis in this. And essentially, the seismic really didn't control most of the wind. The building was controlled by mostly wind for both overall drift and also behavior. In terms of the building acceleration, this is an office and a hotel. So we are within the range, so we didn't need any damper on the building. So essentially, the original design, when we redesigned the building, the client requested that we deliver a building with equal properties to the original design. So when you develop an alternative design, how do you match that? So we did not change the structural system as per se, the arrangement, but we were able to manage that, as we'll see later. Some of the challenges of this project: the building is founded on 138 port piles, varying from 2 to 2.5 meter in diameter. The mega columns, we have 8 of them. They are pretty big. As I mentioned, it's 4.2 by 3.6 meter. And this, the hammerhead, as I mentioned, this area here on top of the core where they concentrated most of the concrete in order to maximize the moment of inertia, they were 7.4 by 4.35 meter. And initially they had a lot of rebar in them with additional stiffness. We were able to take out up to about 4%. It was a nightmare to do the rebar with this kind of arrangement. And then the building essentially linked together with outrigger trusses to the mega column at the 3 levels along the height. And then the spire lifting was very slender and constructability of it was very critical. And we will talk about those a little bit more. This one demonstrates the lateral load resisting system of the spire of the building, which consists of the center core here linked together with outriggers at 3 levels, 40 to 43, 75 to 78, 113 to 116. Because of building stiffness in the north and south direction, which much stiffer than in the east-west direction. Initially, we didn't really want the outrigger, but the client insisted to keep some of them. So we kept the lower one and the upper one only. And now, when you have a building like this, where it's a mix between concrete, composite column or concrete column, and then we have a structural steel element in between the transfer. So, and then the question is, how do you manage the levelness of the floor, the construction sequence to make sure that creep and shrinkage studies and column shortening and everything taken care of. The other challenge that we have on this building, the core at the upper building is asymmetric. So we have a very large lateral deformation due to the asymmetry of the building. And that's another challenge in terms of managing the verticality of the tower. In summary, what we have is a concrete core here, where you use ACS formwork system. We have mega column here, which is mostly concrete. And then we have a structural steel column that span every about 17 floors that get transferred to transfer trusses or belt trusses to the mega column. So as I mentioned earlier, so this kind of arrangement, the floor framing system is mostly composite steel structure. So the differential shortening between the core, the mega column, the structural steel elements here, that was a very big challenge. So we had to do a very detailed construction sequence analysis and compensation program to achieve a leveled floor. And these are just a summary of the lateral systems. This is the first one is the exterior frame, as you can see from the outside, and the east-west section of the core, and then the north-south section where it's locating the center core board, the outrigger at some of these locations. So this is just an overall summary of the lateral system. This is what the exterior envelope looked like for different sections. As you can see, the building all over the place, but at least the column were continuous, and only the structural steel elements that are in red vary. And then we have a very big atrium from level 8 all the way to level 43. It doesn't have really any function. It's just an atrium where the elevator, the observation elevator goes through. The other challenging aspects of this project is related to the hammerhead. As I mentioned, we have the outrigger detail. So we were able to develop a detail made of structural steel element to simplify the construction. We converted everything from structural steel member to more steel elements to take the tension and compression forces in the elements. This is just a picture of what the outrigger looked like. And this is a person here, what you see here. So I developed an alternative design for the outrigger made out of steel plate. Initially, it was casting, but you couldn't really do casting for this kind of size, and we couldn't find anybody who can guarantee the casting. So we looked everywhere, including Spain and Europe, but it's just the time and China, but we weren't able to find somebody who's able to do the casting. So we did it, built up structural steel elements. Now, the mega column is another item, which is a huge, as I mentioned, 4.2 meter by 3.6 meter at the highest level. And as you can see here, if we were to do it manually, one by one, it would have been really difficult. So I developed an alternative design in which we were able to create a pre-assembly for all the mega column, including two structural steel erection columns, small ones. And then we created a template in which we installed all the rebars with the couplers with a perfect matching, pre-matched. And then we were able to erect a pre-assembled mega column, including steel, rebar, angle, embeds, connection to the steel. And we made it as part of the structural steel construction, which made life much easier for both the labor. We also increased the productivity significantly because all the pre-assembly was done on the ground, lifted up in position. So we didn't need a lot of labor. So productivity went up from 250 kilogram per man day to about 2,500 kilogram per man day. And this is just showing some of these member sizes, which I will not go into the detail, but the picture here shows how it works. We have pre-assembled these elements, and we have almost people working at the 3 levels in getting everything done while we're erecting the structural steel work, which made it very, very efficient. One of the challenging aspects that we have this project is the mega column, the hammerhead. As you can see, it's 7.4 meter by 4.3 meter solid concrete element in order to give us the moment of inertia. And initially it has about 4% of rebar. We were able to reduce it by using ultra high performance concrete, or not ultra, high performance concrete up to about 105 MPa with high modulus to about 1%. And so that made life a little bit easier. But the other challenge, because of the size, as you can see, it's a very long element in both directions. So we need intermediate rebar in order to hold the rebar and keep it from sagging. But in addition to that, what we developed an alternative solution, which unfortunately, where we were able to use bow grid system in which we were able to organize this in a much better arrangement. And then instead of having a central core here, we were able to divide it into 2. And we did the very detailed abacus analysis to show the performance of the 2. Essentially, I will not spend a lot of time, but you can see here we have the confinement has to be, the core is much bigger of the concrete that we have to confine. Here, when we did this kind of arrangement, we were divided into 2 smaller cells. And in terms of performance, we did the nonlinear abacus analysis, and we showed that the behavior of these 2 systems are equivalent and no difference in terms of the stress, in terms of behavior. But unfortunately, the consultant at that time felt a little bit uncomfortable using that. So we stuck with the original design. But I think in the future, it is something that the code doesn't address. And I think it's important to, when you have these massive elements, and from a stability standpoint, I think you can have a really nice ring, very tight together, very nicely. Sometimes it's maybe something we can look at in the future and how we can improve the detailing of such massive elements. Now, in terms of the concrete, the planning work, obviously, one of the things, as I mentioned, initially we started with C85 concrete, C70 and C60, but in order to take 14,000 tons of rebar, we used C95 with high modulus. Now, when we did this, the client wanted to guarantee that we have all the aggregate. So we went to a quarry in Johor, and we pretty much bought all the aggregate all at once, and pretty much guaranteed the client that would not be a shortage of it. And at the same time, we wanted, because this is the first time C105 is used, and we use C95, we did not accuse, we did a lot of study correlating concrete strength cylinder versus a cube. we decided to convince the client to just do a cylinder test at the end of the day. But we did a huge amount of work correlating the two together, and using cylinder was definitely much better test than using a cube for this kind of test. So we did a lot of work on this for the planning, trial mixes, mechanical properties, durability test, the creep and shrinkage test, pump simulation test, heat of hydration test, because this is in a very hot climate, and at the same time we have a massive element. So including the raft, including the hammerhead, including the mega column. So procuring these elements become extremely important. And also a concrete mix design, when we designed it, we have the objectives to satisfy all the mechanical properties. Have mass concrete, we need to consider heat of hydration, and also to achieve early strength in 3 days in order to strip the foam and achieve the 3-day to 4-day cycle. And also it has to have a high pumpability. So we use high flow concrete. And the testing that we had done, creep and shrinkage test, a very detailed real-time setup that we did in Korea at our laboratory in Samsung at the time, where we did the creep and shrinkage and elastic shortening test and everything in there. And we also did a pump simulation to look at the friction losses, because we wanted to pump the concrete up to about 500 meter direct without anything. We have a lot of experience in Burj Khalifa when we pumped 600 meter, so we didn't have much of a problem. But we did a lot of work with Lafarge and our concrete team and myself to do a mixed design that is very, very sustainable, high flow, and also low heat of hydration, in which we didn't have the temperature exceeding, around, it was around 70-75 degree maximum. But it was a triple blended cement where we have the OPC less than 50% on that, which I will talk about a little bit more. So we did also heat of hydration analysis for the raft. So because we had, especially for high performance concrete, we dedicated a batch plant on site, where is very close to the site. So we were able to use icing, shaved ice, and also we had a lot of QOQC program to keep the temperature of all the ingredients, all the additives and all that kind of stuff under controlled temperature, and everything was sprinkled and cured and so on and so forth, and protected from sun to keep the temperature down. So we were able to get at mixing is about 25 degrees. For mass degrees, we target 28, but we were achieved less than that because of proximity of that to the site. And we were able to manage the temperature of the raft, the mega column, within 70 degrees centigrade. Now we did these are the concrete mix design that you will see here. We have the same mix design. The only difference is, mostly for low level, where we used 140, 550 binder, almost GGPS 45%, silica fume 10%. So roughly we have 55, and the other were OPC. For CM is the same, but the only thing we changed is really mostly the size of the aggregate type. We kept all the aggregate size to about 13 millimeter. We didn't change those a lot. And we kept the temperature differential within 23 degree. We didn't have any kind of a cracking on the concrete column or the mega column. We cured it properly. This is here, it shows the concrete strength. So the strength was not the issue. We were looking for stiffness. So we agreed to the client, okay, we will achieve 95 MPa cylinder, but actually what we were getting at 90 days, about 110. So we have like about 15 MPa more strength than we needed as target, so the client can feel more comfortable. And for the modulus of elasticity, what you see initially, we targeted about 40. We told them, okay, with 91 days, we will be able to achieve, up to about 45. But reality, at 91 days and above, we were able to achieve up to about 50 gigapascal of modulus of elasticity. And that helped the project enormously in terms of behavior. This is a large-scale mock-up test that we did for the heat of hydration, which I showed earlier. This is also in terms of workability. We have the slump flow targeted at 600 millimeter, and also we just needed to make sure the viscosity was important, and the rheology of the concrete. We did a lot of work, as I mentioned, between ourselves and Lafarge team to make sure that we achieve a very nice system without any kind of segregation or bleeding at all. We also did the durability test, water permeability, initial surface absorption, water absorption, and also chloride permeability and sulfate content. We did all of that, and it's all well below the requirement. The quality control, as you can see here, we have achieved much higher strength than we initially target, up to about 116 MPa. And modulus of elasticity, we were able to achieve up to about 50 gigapascal. On average, I think we're much better than what we started with. This is the pumping test we did for all the different mixes that we have. 133 meter, 369, and 5060, same kind of arrangement, using at the deposit and then at the end to check to make sure that we have all pressure sensors to look at the losses that we have and how to apply it vertically. And this is just a concrete setup that we did at the site, very close to the site for the project. Creep and shrinkage studies, we did all kind of tests, sealed, unsealed, because the concrete stress on average is about 15%, actually, because of the member were controlled by stiffness, really not necessarily strength. But we did the heat of the creep and shrinkage test, and especially the creep at the different stress level, 15%, 25%, and some samples up to about 40%, just to make sure the behavior is okay. And everything was under control temperature, where we have everything. No matter where I am, I can access the room, I can access the temperature inside the room, the humidity, the load cells, the results of the strains for all the samples. So it was a pretty nice setup, a real-time measurement that we have. And so this is something that we did, as I mentioned, sealed and unsealed samples, because we did this in order to do column shortening analysis for the project to make sure that the planning is done right. Now, one of the things that you will see here in terms of modulus of elasticity, we compared what we measured at the 3 days, 5 days, 7 days, all that kind of stuff. We actually have a laboratory at the site where we were able to measure the strength, the modulus of elasticity on site. So we had a lot of flexibility to get a lot of data, and we did a lot of comparison between the cube test and also the cylinder test. So what you will see here, these are the DIS data, and we wanted to select a code for creep and shrinkage. And Eurocode was the best code to use since we have a lot of data to analyze the creep and shrinkage studies. And this is a load comparison. We did, as I mentioned, we promised the client that we will deliver concrete with about 14,000 tons of less rebar, 10,000 tons of steel less, using C105 concrete with equal performance. So as you can see here, we pretty much matched the performance of the building by using high performance concrete and for both the original design for wind and for lateral drift. We also simulated the foundation, actual stiffness of the pile for both aesthetic and dynamic effects. And many of this information came from Arab, so we ran the analysis of it. And as you can see, the original design, we have a displacement of 1.1 meter. The alternative design, 1.1. In the y direction, we have 602. In the alternative design, we had a better behavior because overall it was better. In terms of the drift, we also fully matched the drift between the original design and the alternative design. Inner story drift, also the same. As you can see, we matched both. And in terms of the dynamic stiffness, original was 11.8. We got 11.7, 10.8, 11.1, and 3.9 and 4.16. So we did the testing, the wind tunnel testing related to that. But also, since we use high performance concrete, we were able to reduce the thickness of the wall by about 15%. So actually, that was less load on the foundation. So we reduced the concrete by 15% in the core. We took 14,000 tons of rebar, 10,000 tons of steel, and we were able to have an equivalent performance of the building. The other thing we did is a construction sequence analysis of the project, as you can see here, for many reasons. One is to using because we got now all the concrete tests, the creep and the shrinkage, the modulus, all that kind of stuff. So we included that in all the model. And essentially, we ran the analysis using Eurocode, as I mentioned before, as a base for creep and shrinkage studies. We have the ultimate, creep and shrinkage coefficients that we used in the analysis. And one of the things that really interested me is to correlate, to find out, which model code is the best mode to use. As you can see, when you looked at the creep coefficient in drying condition and also the shrinkage, you can see that the codes are all over the place, So from AASHTO to ACI to CEP to Eurocode to GL2000, PCA, PCI, everything, Korean, Japanese code. And as you can see here, the best fit, because we did the test, was Eurocode. So we use that as a basis for our creep and shrinkage studies. The other thing is we installed a structural health monitoring program on the building, and we were able to measure the actual settlement of the building and correlate because the settlement is very important for also creep and shrinkage. And what we found is the building stiffness was much higher. So we actually, from the settlement analysis, we were able to adjust and correlate what we measured versus what we have, and we use that into the analysis of the project. So what you will see here, at the end of the day, we got a much better building, less deflection, the more than 10% reduction in the overall drift. And also the dynamic frequency of the building went from 11.8 to 10.9 because we get less mass, more or less bigger stiffness than we even originally planned. And also the torsion was much better than what we had originally. Now with the construction sequence analysis, as I mentioned before, we have the mega column, we have the structural steel element, and the construction sequence of those is very important because we were transferring the steel mom to the trusses. And this is a settlement analysis. What you see here, we correlated the settlement analysis for what we had versus what we measured. This is what we measured in reality. And then we kind of adjusted the spring stiffness, and we were able to correlate those. We continued to use those. As you can see, with time, we had the maximum is about 34. Here we have a little bit, 40, 42 or so. And at the end of the day, after November, when the building was completed, we got about 40 millimeter of settlement. In reality, we got about 44, our prediction. And also the lateral displacement of the building, we also correlated that. We have GPS system in which we were tracking the lateral movement of the building on time because of it was very critical for the elevator commissioning and also setting in the right direction. So initially we're predicting about 250 millimeter lateral displacement. Because of the extra stiffness, it was reduced to 180. So we did a lot of studies in terms of creep and shrinkage, but also the compensation, as I mentioned. We have mega column, which is concrete. Intermediate, we have steel. And the question is, how do you keep level the floor? So we spend a lot of time trying to make sure that the differential between the mega column and the steel column remain manageable. And we developed a very detailed compensation program, how to deal with this issue. And we implemented it. We also had what you see here is a very detailed structural health monitoring program. We added accelerometers at the base, accelerometers at every mechanical level and at the top, and also at the top of the spire. We also dynamic strain gauges in some of the steel outrigger to measure both due to gravity and wind. We have tilt meters along the height of the building to measure the building lateral movement with time and make compensation as required. And then also we have strain gauges in the column to measure the total strain, and then also survey method to measure the building actual displacement. We have GPSs and also we have dynamic strain gauges, weather station at the top of the building during construction, and that at the end will be set as part of the permanent stage. I'll just speak very briefly about the construction sequence. What you will see here, as I mentioned, we have train station, we have stadia on a shallow foundation, and we have a very deep basement. So we essentially, but the site was a huge, so we were able to semi top-down construction for the entire site, where we kept the center area open, and then we were able to speed up the construction. Pile testing was done traditional way. That was before our time. It was done by another contractor. This is what the site looked like when we started the project. One of the things in the casting of the raft, because we had like 48 hours to cast 19,000 meter cube of concrete. So you have the weather, the rain, the weather, because we wanted to keep everything temperature down. So we added a temporary cover on top of the building spanning about 80 meter diameter, using fabric, using just wire. We used the crane support structure and the cover dam at the outside to stretch that, as you can see. So it was a fully protected during the whole construction process. So we have a very detailed quality control program. All the trucks come here, all the trucks will be tested. And also when they come here, we have the pump stations all around. So no trucks come here. If the temperature of the concrete was higher than they agreed, we have some layers where we reduce the temperature of the concrete by about 5 degrees at the center to create the concrete mass, where we were able to lower the temperature at deposit to about 20 degrees at the center, where we were able to manage the concrete heat of hydration to within manageable level. And so there was a very strict quality control program. We have nitrogen station here in case we need it. We didn't need it much because we were able to control the temperature pretty nicely. This is here is the nitrogen station that we have. This is the structural system of the roof, in which I used 15 millimeter cable stretching from one side to another, and gave us the flexibility to open and close like a curtain when we need it, and so on and so forth. This is what the site looked like during construction. It was all undercover, and this is just shows you the. So I will just skim through it very quickly because it's time. So so we were working over the weekend for 48 plus hours to deliver this. So this is just, I will skip over these, just the logistic and the planning of the project that we have done. This is shows the semi top-down construction. This is the tower. This is the east part. That's the west part of the project. We have excavator using semi top-down construction that excavate from under while we're going down. So that is some of the images. This is the outrigger here installation, as you can see, with a single plate that extended from one end to another in order not to interfere with the rebar. And this is the mega column construction. Some of these pictures I used to take myself, very close proximity to the site. Used to go to Merdeka 118, and some of them taken by drones. And this is the ACS formwork system. It's a huge core, as you can see. All the equipment, the concrete placing booms, and also the cranes. And this is here demonstrate, in terms of the mega column construction, other structural steel construction. As you can see, we installed, this is pre-assembled, prefabricated mega column that has the rebar, the ties, the connectivity, everything. So minimize the amount of work that needed to be done around some of these elements here. And this is the cladding, finishing of the spire. These are the pre-lifting of the spire, which is a very, very thin spire, not easy. But one of the things we did here, I did propose, we added bracing, additional bracing for the crane, so we didn't have to lift a lot of pieces, and it made things much easier for lifting. This one here is to demonstrate the spire lifting. Pre-assembled, lifted it from the top platform, and then as we go up, we installed the facade, and then did some of the lifting of the spire from within the center up. And we work with Eversandai out of Dubai and Malaysia to work on the structural steel work for this project. It's always very nicely coordinated. And this is here just some at the end of the project before it was all completed. And these are the final images of this project. One of the things that I wanted to say, which I commend the architect, is integration of this project with adjacent project in which they created a promenade that's open to the public. It's like an open park where people can come and enjoy the day. This is the retail. So at a normal day, what it looks like, people can come here with their kids and enjoy both visiting the site, Merdeka 118 Stadium, and we were able to manage the building movement enormously with this project. So these are some of the key people that work on the project. The safety manager, he was amazing. I think to keep everybody safe and away from trouble, we didn't have any major fatal accident on the project. We have some injuries, but nothing major. and he's the CEO. And this is here is our design team that you see here, the key people who really spend day and night. Again, this project we pretty much I would say we spend a lot of time on the project, and we hit by COVID. For 3 years, the project was mostly disrupted. So, this is just a short video that put together by the Star, which is a major newspaper in Malaysia, to summarize the project itself. It's a short one. And it was the first tower to win triple platinum ratings. And with that, I end my presentation, and thank you for your attention, and sorry for not keeping my time. Sorry about that. Yeah. Thank you.
Thank you very much, Ahmad. Probably we will have a few questions. Let's wait a few seconds before having them here. So some things that I was wondering. The first, how many time took to plan the project, to have the project before starting the construction?
Well, I think generally we did in all our projects, when we bid on the project, we have to submit technical submission. So we need to tell the client what we will do. So we develop a very detailed construction method statement for the project execution. But at the same time, it gives the client an overall execution plan, what we are going to do. And we pretty much focusing on delivery of the project, and then we have about 3 to 4 months for bidding. Sometimes you get extension another month here or there, but the 3 to 4 months to put both the commercial offer and also the technical submission. So we need to consider everything we needed to do for this project and price it, right? So it's an intense period of time. But then after that, we need to take element by element and develop the very, very detailed construction methodology. For example, if you look at the raft foundation, the logistic and the planning that it takes to plan 19,000 meter cube of concrete to be delivered in 48 hours, and all the facilities that you have to use, and make sure you develop consistent plan. You got every 1 truck per minute almost, right? So the massive amount that you have to bring in, and to make sure that you get everything a quality control process. It's a very extensive, very systematic, all the concrete testing, whether it's temperature, the flow, everything, and then so it does. And then as we move forward, then we take element by element and detail it in more detail. So we developed a construction method statement for every single trade, practically. Yeah.
Thank you. That's excellent. I see no accidents, and everything was perfect. That's amazing.
Nothing is perfect. There is always some problem here and there, but you overcome,
Yeah. I have some questions
here. The
here.
concrete planning work, actually, we had a lot of challenges, and between us and Lafarge, Holcim at the time, we were able, because this is the first time we use C105 concrete, and the client was very nervous to use to use that. But we told the client, look, for strength, don't worry, okay? We'll give you 15 MPa margin, don't worry, with a cylinder, you know? And then for the stiffness, we also overachieved. So we were very confident in that, you know? And so we did, that's the reason I think in something like this, first time in Malaysia after Petronas Tower, no other company used this kind of concrete, you know? So through collaboration between us and Lafarge-Holcim, we were able to really make a perfect concrete mix that we didn't have any accident in terms of the strength and delivery. Yeah.
Okay. Thank you. There is a question here from Madeleine Taborda. Considering the height of the structure during pumping, did you observe any segregation type? I couldn't see in the composition any kind of additive used.
No, I think we pretty much, as I mentioned, we did a pumping set test. And we didn't have, we did a lot of testing and rheology of the concrete and also the viscosity. So we did a lot of testing to make sure that we didn't run into a problem. And we did all the testing, as I mentioned, in the pump test to make sure, you know, up to about 250 bar, you know, of pressure, and we didn't have any segregation. No bleeding, no segregation.
That's perfect.
Yeah.
We have many comments here congratulating you for the success of the project, the tower, and your presentation from many parts. I should say, while we have more questions, that we have at least 12 countries participating here, probably more, but I'm not sure if, but we have a lot of people from several countries. And is another question from David De Leon. Is there any challenge on the seismic risk of the construction site?
As I mentioned, Malaysia is a very benign seismic. It's a non-seismic area. But however, it's surrounded by Indonesia. Indonesia have a lot of seismic activities, but most of these are far earthquakes. So when we did the site-specific seismic analysis, what we have done is look at the near and far earthquake. Many we have earthquakes that are far, with the building period is more than 11 seconds. So we look at the low frequency content of
tenemos que ver el contenido de baja frecuencia.
And for this reason, the energy was not big enough to influence the. It was considered, but also, as you know, in Malaysia, they require you per British standard to use, you know, what do you call it, nominal, you know, kind of lateral forces based on the mass of the building, and we did that also. Yeah, that's almost, I would say, equal to the earthquake level that we have, but it didn't control. Yes.
Yes, I asked for a question. Now we have a lot of questions here. So
okay.
Let me, but before telling you the questions, Enyo, I think Enyo wants to say something. Enyo, please.
Okay, thank you, Pedro. Very interesting presentation, Dr. Ahmad. Very, very interesting. I would like to know about some dates that you are presenting in some tables related to resistance, strength, resistance. I saw that was related not to 28 days, but in 56 days, or include 91 days. My question is, the designer or the designer was thinking when changing this date in the layer de Tringit formation, or if have another contribution when you move this date.
otra contribución.
No,
cuando
I
se
think
pasa en esta
as I did
fecha.
when we did the concrete planning work, there are several things that we need to consider. One is we need to strip the foam as soon as possible. So we need to gain 10 to 15 MPa before we take the foam work out, right? Because we need to go into the next cycle. Fortunately, with this kind of concrete, we were able to achieve up to about 20 MPa without problem after 1 day. And then we did the testing for 3 days, and then we did the testing at 28 days. So the 28-day test is important for original design requirement, right? That we set on the project. However, in these buildings, you know, when you are at 28 days, the building is 100 stories. So it doesn't, the stress level is so low, it doesn't make any sense. You know, I think usually, even in Burj Khalifa, when I specified the requirement, we went to 56 days or 91 days to achieve full strength and full modulus. But usually modulus, as you know, within 3 to 7 days, you must develop most of the modulus that you really needed in many areas. You know, modulus is pretty good. At 28 days, 51 days is we're looking at the modulus. That's it. I mean, it wasn't, and that's what we were looking at. And also for the heat of hydration analysis, when you strip the foam, we need to make sure that we have enough strength that it doesn't create any kind of surface cracking in terms of curing and other things. Yeah.
Thank you, Ahmad.
Makes sense?
Thank you.
We have another question here. Was there only one pumping station or more because of the height of the building?
No. We have for as you can see, we have 4 pumping stations, but each pump, it has 2 trucks if needed. When we did the raft, we have almost close to 20 stations, right?
Okay.
And then because it's huge. But when we did the concrete, we kind of do the columns and the slabs, and we kind of work 24 hours at different times. But for massive elements, we try to do most of the concrete casting at night. So we have a lower temperature, and also we don't have a lot of heat in there, as much as we can.
Yeah, perfect. There's another question from Victor Hernandez. Congratulations. What was the main composition of the mixture design to reach that compressive resistance?
Well, 2 things. One is obviously, as I mentioned, we use GGBS, about 45%, 10% microsilica, and the rest is OPC, but also the type of aggregate we use, which is basalt. And then also additional additives that we work very closely with Lafarge Holcim, you know, to gain the durability. And these are the main compositions.
Yeah. Another question from Francisco Centeno. For the foundation of the piles, did the constructors verify the integrity of the concrete piles with non-destructive tests as cross-hole sonic logging? Sonic, not sonic, but sonic.
Yeah. The piles were done by a different contractor, local contractor. And then when we came to the site, yes, we did non-destructive testing. And there were some observation that the client has to adjust and take care of. Yes, we did. So we did they did their own testing, but we also, before proceeding with the construction, we also did our own non-destructive testing. And we use Figaro to do random testing to make sure that, and in the testing, yes, there was sonic testing that was done for the plants. Yes.
Perfect. I think this is the last question. Yeah. What was predominant on the design, seismic or wind?
As I mentioned in my presentation, the wind, for sure. Seismic is a very low seismic. A lot of time the shear at the base of the building and the spire, we have to be careful because of the whiplash effects. So we do have to pay attention to the base shear. Generally, because of the higher modes of seismic, you end up getting more shear sometimes than wind. We have to account for that, but also the spire at the top, which is very flexible. So we have to take care of that seismic. Yes. Yeah.
Perfect. Yeah. Ahmad, if you let me, I would like to say to the audience that we recently published a special issue of Revista El Compact, where several articles. One of these beautiful articles is that from Ahmad regarding this tower, the Merdeka Tower. So I invite all of you to check this article because it's very beautiful. And of course, we have a special person here in the audience, Dr. Surendra Manreka, who introduced me with Ahmad, a very nice person. He is connected from India. It's very late in India. Surendra, welcome to this conference. Surendra was the invited editor for this special issue that I am saying. So congratulations for the success, not only in the conference, but with this special issue, Surendra. And thank you, Ahmad, for publishing your article there and for sharing with us your experiences and especially the challenges that you set. If there is no more questions, I would like to give the word to Javier Angeles and then Enyo. And finally, I would say some announcements.
Gracias, ingeniero Pedro. Y bueno, pues no me queda más que agradecer a todos los que se conectaron a la sesión. Muchas gracias por acompañarnos por más de una hora en esta sesión tan apasionante. Lo leemos por sus comentarios acá en el chat. Muchas gracias por seguir los Senior Webinars. Gracias a Enio, Pedro, Alexia, a todo el equipo de Alcompact. Y también muchas gracias a Ahmad por esta excelente presentación. Thank you so much, Ahmad.
Well, it's my pleasure. Thank you very much for the invitation. But one thing I wanted to tell the audience that they would be, since they are into concrete, I think there was one paper that I published related to Burj Khalifa, structural health monitoring program that talks about concrete planning work, and it's also talking about the actual behavior of the building. And I think you will find it extremely valuable because it does correlate. Sometimes you design and you build, but you don't know what you really got. And with this building, both of them, we did the structural health monitoring program. We were able to correlate what we designed versus what we built in terms of the dynamic properties, in terms of creep and shrinkage, in terms of building properties. And that is something I think they may find very valuable in addition to the paper that Pedro mentioned. So thank you very much for the invitation. And if you guys have any questions, and feel free to reach out and through Mr. Pedro, and we'll be happy to answer any of them. Thank you so much. And also, Mr. Surendra, thank you very much for organizing this meeting with Mr. Pedro. Thank you so much.
Enyo, please. Yes, your microphone is closed.
Ok, em nome de Alcompact Internacional, nos encanta agradecer a toda a audiência, muito mais de 100 pessoas, 110, 115 pessoas han estado con nosotros, y luego muchas más pueden ver este video que se queda grabado. Es un placer inmenso tener la oportunidad de escuchar el doctor Ahmad Abdelrazaq sobre esta fantástica obra. Thank you so much, Dr. Ahmad Abdelrazaq, for this fantastic presentation. Y agradecer también a Holcim, que nos ha dado la oportunidad de compartir con toda la audiencia y nuestros socios de Alcompact Internacional, los que vienen de las Alcompacts nacionales que están en toda la Iberoamérica. Muchísimas gracias.
Gracias, señor. Bien, yo solamente quería, antes de clausurar, invitarles a todos. Recuerden que la siguiente semana tenemos nuestro 7º Seminario Internacional de Jóvenes al Compact Penetron, que pronto, también en la otra semana, estaremos empezando nuestro 3er curso de línea de al Compact. Hay una generación completa que viene en camino, pero pueden unírsele otros, ¿verdad? Les invitamos a consultar la página web que ya se encuentra actualizada con respecto a estas actividades. Y también invitarles porque pronto también tendremos otro seminario de puentes con la sociedad, donde nuestro ponente de la vez pasada va a cumplir su palabra de hablarnos de Leonardo da Vinci. Eso va a ser algo impresionante, ¿verdad? Así que muchísimas gracias a todos por estar pendientes de todas nuestras actividades. Thanks a lot, Ahmad, again, for your kind participation. A los miembros de Alcopat, los recordamos que el mes de junio, ¿verdad? Sigue vigente los descuentos para inscribirse al Congreso Compact 2025, 90 años del Instituto Torroja, 35 años de congresos de Compact y 15 años de la revista El Compact que estaremos celebrando en Madrid del 24 al 26 de septiembre. Aprovechen estas oportunidades. 26 de junio, el CIHAB, nos comenta Alexia, a partir de las 8 de la mañana, tiempo de México, ¿verdad? Okay, we are going to finish our senior webinar. Thanks a lot, Ahmad. Thanks a lot also to Surendra Manrekar for being the invited editor of Revista Compa and for introducing us with Ahmad. And you are kindly invited to all of our activities, Ahmad, of course.
Thank you very much.
A lot.
Yeah, you got a great audience. Thank you so much. Yeah, take care. Yeah,
almost 15. I said I identified 14 countries. 14 countries.
Wow,
from
amazing.
Latin America.
Amazing.
Amazing.
Thank you so much. I hope some of you will be able to visit this project. It's pretty exciting. So, yeah.
Okay.
Yeah. Take care.
See you the next time.
Okay.
Bye, guys.
Bye. Bye.